Welcome to section 2.3, quadratic functions and their zeros. All right, let's go into our definition for a quadratic function. So a quadratic function is a function of the form f of x equals ax squared plus bx plus c, where a, b, and c are real numbers and a does not equal 0. The domain of a quadratic function consists of all real numbers. So list some examples of quadratic functions. Okay, so let's say we have f of x equals 7x squared minus 3x plus 1. G of x equals negative 8x squared plus 4. And h of x equals 3 over 2 x squared plus 1/3 x. So all of these are examples of quadratic functions that are written in this form. So in other words, a quadratic function is a second-degree polynomial in one variable. So all of these functions, all of these examples have only one variable, x, and it's second degree because the highest exponent in each of these functions is 2. Okay? So a quadratic equation is an equation equivalent to the form ax squared plus bx plus c equals 0, where a, b, and c are real numbers and a does not equal 0. So now let's list some examples. So we're going to now write quadratic equations. So we'll have 7x squared minus 3x plus 1 equals 0, negative 8x squared plus 4 equals 0, and 3 over 2 x squared plus 1/3 x equals 0. Okay, so the difference between the two is that a quadratic function has the function notation f of x, g of x, or h of x, as we saw in the previous slide. However, on this slide, we're looking at quadratic equations. And this is where we're going to set an expression equal to 0 or equal to a value. So why do both definitions above require that a does not equal 0? And what type of function would f of x equal ax squared plus bx plus c be if a equals 0? Well, both definitions require that a does not equal 0, and I'll write it up here at the top for us. So we had our quadratic function, x squared plus bx plus c, and our quadratic equation. Now, if a equaled 0, the leading term here, ax squared, would disappear because anything times 0 is 0. So that would just leave us with bx plus c in both the function and the equation formats. Now, bx plus c is no longer a quadratic function. Bx plus c is now a linear function, so it's written in the form y equals mx plus b. So if a equals 0, we've now changed our function or equation to a linear function or equation. So that's why we do not want a to equal 0. And it's a requirement when working with quadratic functions and quadratic equations. So a quadratic equation written in the form ax squared plus bx plus c equals 0 is said to be in standard form. Sometimes a quadratic equation is called a second degree equation because when it is written in standard form, the left side is a polynomial of degree 2. All right. So recall that solving the equation f of x equals 0 is equivalent to finding the zeros of f, and it is also equivalent to finding the x-intercepts of the graph of y equals f of x. 4 methods for solving quadratic equations will be presented: factoring, the square root method, completing the square, and the quadratic formula. So we're going to go through all 4 of those methods in this lesson. So let's look at the first method. Find the zeros of a quadratic function by factoring. So solving equations by factoring relies on the zero product property. So let's review what that means. So the zero product property states that if A times B equals 0, then A equals 0, or B equals 0, or both. So in this example, we're now going to find the zeros of this quadratic function, and we're going to list any x-intercepts of the graph of f. Okay. So to find the zeros, we are going to need to place this quadratic function in factored form. Okay. So we're going to first set f of x equal to 0. So we would have 2x squared minus 5x minus 3 equals 0. Now we're going to multiply the leading term 2 by 3 to get us 6. So we multiply the leading term 2 by 3 to get us 6. And 3 is the constant term. So now we need 2 values that multiply to get us 6, but add to get us negative 5. Okay, and this would be actually a negative 6 because 2 times negative 3 is negative 6. So the 2 values that multiply to get us negative 6, but add to get us 5 is going to be negative 6 and 1. Negative 6 times 1 is negative 6, but if I were to add these 2 values together, I would get negative 5. Okay, so I can now rewrite this quadratic equation where my negative 5x is now split into 2 terms. So let's write that out. So negative 6x plus 1x. Okay, so I'll restate what we just did. So we multiplied 2 times negative 3 to get negative 6. Now I need to think of 2 factors of negative 6 that multiply together to get negative 6, but add to get negative 5. Those 2 values were negative 6 and 1. Negative 6 times 1 is negative 6. Negative 6 plus 1 is negative 5 because that one is positive. So now I can rewrite my quadratic equation with negative 5x, my linear term, as 2 terms. So now I'm going to bring down the other terms. So I have 2x squared here, minus 3 here, equals 0. Okay. So I'm going to remove this bracket here. Excuse me. All right. So next, we are going to group the first 2 terms. And we're then going to group the second two terms. And we're now going to factor out the GCF, so the greatest common factor. Okay, so the greatest common factor between 2x squared and negative 6x is 2x. That leaves me with a binomial x minus 3. The GCF between 1x and negative 3 is a positive 1 because they're both prime, which then leaves me with x minus 3. So the goal is to get the same binomial when you factor out the GCF from both groupings. If you are unable to get the same binomial, then you might need to rearrange your two terms that you created. So I would place the 1x where the negative 6x is, and then move the negative 6x where the 1x is. Okay, so once I now have my two new terms, I can now factor out the GCF again between them, which is x minus 3, and that leaves me with 2x plus 1. And so now I have my quadratic equation written in factored form. So once it's in factored form, I can now use the zero product property to help me find my zeros. So to do that, I'm going to set each factor in my factored form to 0. So this would be x equals 3 and solve. So 2x plus 1 equals 0. So 2x equals negative 1 and x equals negative 1/2. So my zeros are going to be negative 1/2 and 3. My x-intercepts are going to be the points negative 1/2, 0, and 3, 0. Okay. Alrighty. So sometimes the quadratic expression factors into two linear equations with the same solution. In such cases, the equation is said to have a repeated solution. This solution is called a root of multiplicity 2 or a double root. So let's do an example together. So we're asked to find the zeros of g of x equals 4x squared plus 9 minus 12x. List any x-intercepts of the graph of g. So the first thing that I notice in this problem for g of x is it's not written in descending order. So to help me clearly solve this problem, I'm just going to rewrite it in descending order. So I'll have g of x equals 4x squared minus 12x plus 9. Okay, so now that it's in descending order and I can clearly see my a, b, and c, I'm now going to solve. So I'm going to set g of x equal to 0. Then I'm going to write it as a quadratic equation. So 4x squared minus 12x plus 9 equals 0. I'm going to multiply my leading coefficient and my constant, and that's going to give me 36. So I need two values that multiply to get me 36, but add to get me negative 12. And that's going to get me the two factors, negative 6 and negative 6. Negative and negative make a positive, so that would give me a positive 36. But if I add them together, that would get me negative 12. So those are the two values that I need. So I'm going to put an x there because I'm rewriting negative 12x as negative 6x minus 6x. And then I'll bring down my other terms. So now I'm going to group together the first two terms, group together the last two terms. I'm now going to factor out the GCF. So in the first one, that would be 2x, which leaves me with 2x minus 3. In The second grouping, I'm going to factor out GCF, which would be 3, the greatest common factor, and that leaves me with 2x minus 3. So I'm dividing both terms by that negative 3. So now I went from 4 terms to 2 terms, and between these 2 terms, our GCF is 2x minus 3, which leaves us with 2x minus 3. Okay, so now I have my quadratic equation written in factored form. So to find my zeros, I'm now going to set the factor equal to 0. Since both factors are the same, I only need to solve for x one time. So I move the 3 to the other side and then divide it by 2. So my 0 for this quadratic function is 3 over 2. And my x-intercept will be the point 3 over 2, 0. Alrighty. Objective number 2. Find the zeros of a quadratic function using the square root property or square root method. The square root method states that if x squared equals p and p is greater than 0, then x equals the square root of p, or x equals the negative square root of p. So we sometimes write this as plus or minus square root p. Okay? The two solutions to x squared equals p are usually abbreviated as x equals plus or minus the square root of p. Okay? So, for example, say I have x squared equals the square root of 9. Then I take the square root of both sides to, oh, sorry, let's remove that square root. We haven't squared yet. Will make more sense this way. All right, let's say x squared equals 9. Then I would take the square root of both sides in order to eliminate the square on the x. This will then get us x equals plus or minus the square root of 9. I did write a p there, didn't I? Let me rewrite that as a 9. Maybe I was looking at the p above. I want to make sure it's not confusing to you. All right, so I took the square root of both sides, right? And now I can simplify my answer. So x will equal plus or minus 3, because the square root of 9 is 3. Okay. So we're going to now apply this to solving for a quadratic function. Okay. So we want to find the zeros of each of these functions. So the first thing that we want to do is set our function equal to 0. So we're going to set f of x equal to 0. So then x squared minus 18 equals 0. We want to get x by itself. That's what we're solving for, the unknown variable. So we'll add 18 to both sides. To eliminate the square on our variable, we have to take the square root of both sides. When we take the square root of both sides, we'll have plus or minus. Let me show you that middle step, actually. I want to show you the middle step. So take the square root, both sides. That will give us x equals plus or minus the square root of 18. Now we want to simplify this a little bit, so we need to simplify the square root of 18. It's not a perfect square, but in order to simplify it, we can identify the perfect square that is a factor of this square root. So let's do that. So we have the square root of 18, and the perfect square that is a factor of 18 is 9. Because 9 times 2 is 18. Then I can split that square into 2 squares. And this will then simplify to 3 square root 2. That's how I simplify my square root of 18. And so x will equal plus or minus 3 square root 2. Okay. All right. So for my zeros, that's what our problem asks us to do. I would have negative 3 square root 2 and a positive 3 square root 2 for my zeros. All right. Let's do the next one. G of x equals the quantity x minus 1 squared minus 4. So g of x then will equal 0. That's the first step. Then we'll have x minus 1 squared minus 4 equals 0. We want to get x by itself, so we're going to need to undo some operations here. So first we'll add 4 to the other side. So that would be the quantity x minus 1 squared equals 4. To get rid of the square, we are going to take the square root of both sides. In taking the square root of both sides, we've now eliminated that square. So that leaves us with x minus 1 equals plus or minus the square root of 4, which is 2. To get x by itself, we're now going to add 1 to the other side. So x equals 1 plus or minus 2. Okay. Now we have x by itself, and if we evaluate the right-hand side here, x can equal 1 plus 2, or x can equal 1 minus 2. Now 1 plus 2 is 3, and 1 minus 2 is minus 1. So our zeros for this quadratic function are negative 1 and 3. Awesome. So in order to use the square root property or method, we need to have all the variables in the equation contained within a square, such as the two forms in the previous example. If this is not the case, we can get a quadratic function in one of these forms by using the method of completing the square. So in objective 3, we're now going to find the zeros of a quadratic function by completing the square. So for this example, we're asked to find the zeros of f of x equals x squared plus 6x minus 72 by completing the square, and then list any x-intercepts of the graph of f. All right, so we're going to walk through the beginning portion of this process of completing the square together on this slide, and then on the next one, we'll finish it off using the square root method. All right, in completing the square, we are, like the rest, setting f of x equal to 0. So x squared plus 6x minus 72 equals 0. Okay. Now, according to our directions here, it says we need to identify the coefficient of the first degree term, namely b. Okay. So we need to identify where b is, and I'm going to put a star there. Okay. Now, once you've identified b, your next step that isn't mentioned here, but what I want you to do is I want you to move your constant term to the right-hand side. So we'll have x squared plus 6x equals 72. Okay. This will allow us to complete the square on the right-hand side. Notice that this right-hand side is set up the same way as our directions for completing the square of x squared plus bx. That is key. It is very important that you move all constant terms to the right-hand side so that the left-hand side has your second degree term and your linear term. So your x squared and your x term. Okay. So now that this is separated, we can now multiply b by 1/2 and then square the result. So we're going to take 1/2 times b, which is 6, and we're going to square it. So 1/2 of 6 is 3, squared equals 9. So now that we have completed step number 2, we are going to add this 1/2 b squared to the linear, sorry, not the linear side, but the side with our terms, and we're going to add it to the side with our constant. So we're going to, in other words, add it to both sides. So we have x squared plus 6x plus 9 equals 72 plus 9. So this was us trying to find our constant that will allow us to complete the square on the left-hand side of our function. Okay, so now we can write the left side in factor form because it's a quadratic, and the right-hand side we can simplify. So in writing this in quadratic form, or in factor form, we need two values that multiply to get us 9, add to get us 6, and that's going to be 3. Then 72 plus 9 is going to get us 81. So this is the same thing as x plus 3 squared equals 81. All right. Note that the term that you're trying to find in your factored form is always going to equal the term that you squared when finding b. That's a neat little trick. All right, so now that we have our function, our equation in the square root method format, we can use that method to find our zeros and our x-intercepts. So let's do that. So we have x plus 3 squared equals 81. So we'll take the square root of both sides. Okay, then we'll simplify. So we'll have x plus 3 on the left-hand side, and then plus or minus 9 on the right-hand side. To get x by itself, we'll subtract 3 on both sides. So we will have x equals -3 plus 9, and x equals -3 minus 9. So -3 plus 9 is going to get us 6, and -3 minus 9 is going to get us -12. So our zeros are the values -12 and 6, and our x-intercepts are the values, or I guess you should say the ordered pairs, -12, 0, and 6, 0. Alrighty. So something to keep in mind, so a caution for you. To use the 1/2 b squared to complete the square when solving a quadratic equation, the coefficient of the x term must be 1. If it is not 1, then divide both sides of the equation by the coefficient of x squared. So let me just explain that a little bit. So let me get my pointer here for us. So in this problem, our leading coefficient was 1. If this was not 1, say it was 2, all right? In order to do this process of completing the square, I would have to get rid of the 2 as the leading term. In order to do that, I would have to divide all of these terms by 2. In dividing all of these terms by 2, I would then have 1 as my leading term, which will allow me to go through this process of completing the square. Okay, so let's do an example. Find the zeros of f of x equals 2x squared plus x minus 1/8 by completing the square. List any x-intercepts of the graph of f. So first, we are going to set f of x equal to 0. It's the first thing we do. Then we are going to take our function and write it out and set it equal to 0. I see here that my leading term has a 2, so I'm going to divide all of my terms by 2. So 2x squared divided by 2, x divided by 2, and then I have 1/8. Dividing it by 2 is the same thing as multiplying it by 1/2. And then 0 divided by 2 is just 0. So now we can simplify. So we have x squared plus x over 2 minus 1/16 equals 0. So now I need to write this in the correct format for completing the square, which would be x squared plus x over 2 equals 1/16. Remember, you always want to move your constant to the right-hand side. So now I'm going to find 1/2 b squared. So my b here is going to be the value 1/2. Remember, this can be written as x squared plus 1/2 x equals 1/16. Both methods are correct. So in finding my 1/2 b squared, this would be 1/2 times 1/2 squared, which would equal 1/4 squared, which would equal 1/16. Okay. So now I'm going to be adding 1/16 to both sides. So I'll have x squared plus 1/2 x plus 1/16 equals 1/16 plus 1/16. Okay. So now we can simplify the right-hand side by combining like terms, and then we can write the left-hand side in factored form. Okay. So let me just rewrite that here for us. X squared plus 1/2 x plus 1/16 equals 1/16 plus 1/16. So in factored form, this would be x plus 1/4 squared equals 2/16. Okay. Then we can take the square root of both sides. Okay. The square root on the left-hand side cancels the square. The right side simplified is going to be plus or minus the square root of 2/4. To get x by itself, I'm going to subtract 1/4 to the right-hand side. So now I can rewrite this expression with a common denominator. So x equals -1 plus or minus the square root of 2 over 4. Okay. Note for this square, just so that you have it in your notes, the square root of 2 over 16 can be written as the square root of 2 over the square root of 16. Square root of 2 is not a perfect square, but the square root of 16 is, which gives us 4. Okay, so that's how I got that value. All right. So our zeros are going to be -1 plus the square root of 2 over 4 and -1 minus the square root of 2 over 4. Our x-intercepts are going to be the points -1 plus the square root of 2 over 4, 0, and -1 minus the square root of 2 over 4, 0. Alrighty. Objective 4. Find the zeros of a quadratic function using the quadratic formula. So consider the quadratic equation ax squared plus bx plus c equals 0, where a does not equal 0. If b squared minus 4ac is less than 0, this equation has no real solutions. If b squared minus 4ac is greater than or equal to 0, the real solutions of the equations of this equation is given by the quadratic formula. X equals -b plus or minus square root b squared minus 4ac all over 2a. If you remember this equation from grade school, you might have had a ring to it. I think it went like x equals -b plus or minus square root b squared minus 4ac all over 2a. Hopefully that doesn't come up in your dreams. But anyway, every time I go through the quadratic formula, that song always pops into my head. I just remember it from grade school and it's still stuck in my memory. Anyway, all right. The quadratic equation is given by this formula. All right, so we're going to use this formula to solve quadratic functions. But the quantity b squared minus 4ac is called the discriminant of the quadratic equation because its value tells us whether the equation has real solutions and how many solutions to expect. So for a quadratic equation, ax squared plus bx plus c equals 0, if b squared minus 4ac is greater than 0, then there are two unequal real solutions. Therefore, the graph of f of x equals ax squared plus bx plus c has two distinct x-intercepts. If b squared minus 4ac equals 0, then there is a repeated real solution, or a root of multiplicity 2. The graph of f of x equals ax squared plus bx plus c will have one x-intercept at which the graph touches the x-axis. If b squared minus 4ac is less than 0, then there is no real solution. Therefore, the graph of f of x equals ax squared plus bx plus c will have no x-intercepts. Alrighty. So in our first example for this objective, we're asked to find the real zeros, if any, of the function f of x equals 3x squared plus 5x minus 3, and then list any x-intercepts of the graph of f. Okay, so just like in the previous objectives, the first thing we're going to do is set f of x equal to 0. Okay? So that will give us 3x squared plus 5x minus 3 equals 0. Okay? Now we need to identify our a, b, and c so that we can use the discriminant and the quadratic formula to help us find our zeros and x-intercept. So according to this problem, our a is going to be 3, our b will be 5, and our c would be negative 3. Okay? So the discriminant, b squared minus 4ac, is going to be, let me write that under actually, not across, so that you can see it clearly. All right, it's going to be 5 squared minus 4 times 3 times negative 3. 5 squared is 25. Negative 4 times 3 times negative 3 is going to be a positive 36. 25 plus 36 is going to get us 61. Now 61 is positive, meaning it's greater than 0. So that means there are two unequal real solutions. Okay? So now we can use the quadratic formula to help us find those two unequal real solutions. In our quadratic formula, negative b plus or minus square root b squared minus 4ac over 2a. We know what the b squared minus 4ac is because we've already identified it. So we can just substitute in our values for our unknowns. So b is 5 plus or minus the square root of 61 over 2 times a, which is 3. Okay. Now simplifying this, we have negative 5 plus or minus the square root of 61 over 6. 61 is not a perfect square, so our zeros would be negative 5 plus the square root of 61 over 6 and negative 5 minus the square root of 61 over 6. And our x-intercepts will be the points negative 5 plus the square root of 61 over 6, comma 0, and negative 5 minus the square root of 61 over 6, comma 0. All right. So let's now find the real zeros, if any, of the function f of x equals 2x minus x plus 1. List any x-intercepts of the graph of f. So we'll set f of x equal to 0. So 2x squared minus x plus 1 equals 0. We're going to now find the discriminant. So let's first identify our a, which is 2, our b, which is negative 1, and our c, which is 1. So b squared minus 4ac is what we're trying to evaluate. B is negative 1, a is 2, and c is 1. So simplifying, we have 1 minus 4 times 2 times 1, which gets us minus 8. 1 minus 8 is negative 7. Now, -7 is less than 0, which means there are no real solutions for this problem. So we have no real zeros and we have no x-intercepts. So not applicable, or we say does not exist. And then x-intercepts is the same thing. Alrighty. Awesome. So in general, in finding the zeros or x-intercepts of the graph of a quadratic function, you first are going to be given f of x equals ax squared plus bx plus c, and you're going to write the equation as ax squared plus bx plus c equals 0. Make sure it's in descending order. Then you are going to identify A, B, and C. Okay? Then you will evaluate the discriminant. Discriminant. It's like a spelling bee word. B squared minus 4AC. Okay? If the discriminant is negative, the equation has no real solutions. No real zeros and no x-intercepts. Remember, intercepts are where the graph crosses its respective axis. If the discriminant is non-negative, the equation has real solutions, real zeros, and x-intercepts. Okay? And this is where you will use either the factoring method, that's where you use the zero product property, completing the square, or the quadratic formula. Quadratic formula to solve for x. Okay, so those are your steps for finding the zeros and the x-intercepts of a graph of a quadratic function. Okay, all right. Objective 5, find the point of intersection of two equations. So in applications, we are often interested in knowing where two equations are equal to each other. For example, if R equals R of X, which represents the revenue for selling X units of a product, and C equals C of X, which represents the cost of manufacturing X units of the product, then knowing the number of goods for which cost equals revenue might be of interest. So finding this requires solving the equation R of x equals C of x. Each solution to this equation has a geometric interpretation. It is the x-coordinate of a point where the graphs of the two functions intersect. Okay. So, for this example, if f of x equals negative 2x plus 1 and g of x equals 3x plus 2, solve f of x equals g of x, and then at what points do the graphs of the two functions intersect? Okay. So we are asked to solve f of x equals g of x. So we're going to take the function f of x and set it equal to g of x. So f of x is negative 2x squared plus 1, and g of x is 3x plus 2. Okay. So now let us get all of the like terms together. We have negative 2x squared minus 3x minus 1 equals 0. So to move forward into a specific method, we want to make sure that our leading term here is positive. So we're going to divide every term by negative 1 to make this leading term positive. So dividing by negative 1 changes all of the signs. So this is 2x squared plus 3x plus 1 equals 0. Now I can take the leading term and the constant, and that gets me 2 when I multiply together. So I need two numbers that multiply to get me 2, but add to get me 3. And that's going to be 2 and 1. So I can now rewrite 3x as 2x plus 1x. Bring down my other two terms. Then I'll group together the first two terms, group together the last two terms, and factor out the GCF. First grouping, the GCF was 2x, which leaves me with x plus 1. Second grouping, the GCF is 1, which leaves me with x plus 1. Remember, the goal is to get the same binomials when you factor out the GCF. So now I have two terms, and their GCF is x plus 1, which leaves me with 2x plus 1. Okay. So now that it's in factored form, I can use the zero factor property, and I can set each factor equal to 0 and solve for x. So x plus 1 equals 0 is the first one, which gives me x equals negative 1. And then 2x plus 1 equals 0 is the second. Solving for x, I get x equals negative 1/2. Okay. So now that I have the x values, I now need to determine what the y coordinates are. Because remember, I'm trying to find the points of the graph. Okay. So since I have two x coordinates, I need their associated y's. Since I've set both functions equal to each other and solved, I can use either function to help me find my y's. Okay. So between the two, I'm going to choose the linear function g of x to help me find my y coordinates. So I'm going to evaluate g at negative 1. So I'll substitute 1 in for x. And that gets me negative 1. And then I'm going to substitute in 1/2 for x. And simplify. And I get 1/2. Okay. So the graph intersects at 2 points. The first point is -1, -1. And the second point is -1/2, 1/2. And that is our answer to this problem. All right. Objective 6, solve equations that are quadratic in form. So a tip for this section, we have only found zeros of functions that are in the form f of x equals ax squared plus bx plus c. However, there are times when we might be asked to find the zeros of a function that is not quadratic, but one that can be transformed into a quadratic function with an appropriate substitution. For example, the equation x to the fourth plus x squared minus 12 equals 0 is not quadratic. We know it's not quadratic because the leading term has a power of 4. However, letting u equal x squared allows us to write this equation as u squared plus u minus 12 equals 0, which is quadratic in u. If an appropriate substitution u can be used to transform an equation into one of the form au squared plus bu plus c equals 0, where a does not equal 0, the original equation is called an equation of the quadratic type or an equation quadratic in form. All right. Let's do a couple examples. Our first one, find the real zeros of this function f of x plus 2, the quantity, squared, plus 7 times the quantity x plus 2 plus 12, and then find any x-intercepts of the graph of f. Okay. Caution, do not stop after finding the values for u. Remember to continue solving for the original variable. So we're going to approach this in the similar fashion as we did previous quadratic equations. So we're going to set f of x equal to 0. That's the first thing. So x plus 2 squared plus 7 times x plus 2 plus 12 equals 0. Okay. Then we are going to rewrite it now in terms of u. So we're going to set u equal to x plus 2. Okay, which means u squared is going to be x plus 2 squared. All right. So rewriting this in terms of u, I now have u squared plus 7u plus 12 equals 0, which is written in quadratic form. So in factoring the quadratic, I now have to find two terms that multiply to get 12 but add to get 7. So that would be 3 and 4, and they're both positive. Okay. So now I can set both of my factors equal to 0 and solve. So u plus 3 equals 0, so u equals -3. U plus 4 equals 0, so u equals -4. Now that I know what u is, I can take both of these two values and plug it back in to my u equation to find x. So remember, let me star that for you. U equals x plus 2. So since u equals x plus 2, I can take -3 equals x plus 2. Actually, let me rewrite it the other way so that x is on the right-hand side. Okay, so u equals x plus 2, and I can now set it to -3, x plus 2, and I can set it to -4, and then I can solve for x. So x equals -5, and x equals -6. So my zeros are going to be the values -6 and -5, and my x-intercepts are going to be the points -6, 0, and -5, 0. So just don't forget that once you have your quadratic that was written in U form solved, you have to now take those values of U and substitute it back into the equation for U to solve for your original unknown variable. Okay, that's very, very important. And something you might forget. So I just wanted to remind you. All right, our next equation. Find the real zeros of the function g of x equals x plus the square root of x minus 2, and then find the x-intercepts of the graph of g. So we'll set g of x equal to 0. So that means x plus the square root of x minus 2 equals 0. So u is going to equal the square root of x. So u squared is going to equal x. Because if I square a square root, it cancels, just like if I square root a square. Okay? So rewriting this, I now have u squared, because x equals u squared, plus u minus 2 equals 0. So now I can write this in factored form. So I need two values that multiply to get me -2, but add to get 1. So I have -1 plus 2. So now I can solve for u. So I'll have u plus minus 1 equals 0, so u equals 1. And then I have u plus 2 equals 0, so u equals -2. Now I need to back substitute. So I need to find my unknown variable from my original equation. So u equals the square root of x. Okay, so the square root of x equals 1, and the square root of x equals -2. So to get x by itself in the first equation here, we are going to square both sides. So the square root of x squared and 1 squared will be x equals 1. Then the square root of x equals the square root of, the square root of x equals -2. You would think that you could just square both sides, but we have to look at this equation a little closer. Okay, the square root of x equals -2. Well, the square root of any real number is never negative. It's always positive. So this equation gives us an imaginary value. So there is no real solution for this equation. So no real solution. Okay? So we only have 1 0 for this problem, and that's 1. And we only have one x-intercept, which is the point 1 0. Okay, that is our answer to a problem. All right. Well, that concludes section 2.3.